use in the space program. However, there have been several waves of interest in hydrogen for other reasons. Interest to the broader community, way beyond the space program. In the 1970s, the oil crisis drove a search for alternative fuels, including hydrogen. But then oil availability increased and its price dropped, and the interest in hydrogen kind of subsided. And then in the year 2000, or the 2000 timeframe, there was another wave driven by the interest in electric cars, driven by fuel cells, which run on hydrogen. The rise of batteries reduced the interest in fuel cells and hydrogen. Now there is a new driving force, which is climate change. And the developing countries have decided to decarbonize by 2050. And that really makes everybody look for hydrogen. And the question at hand today is, what is the potential of hydrogen in aviation? Where will we see it develop, and in what time frame? With that, I'll turn the floor to Bruce, and you got 15, 20 minutes. Please go ahead. And Allison, you could switch, give him the screen now. How do I do that for my part?
Just stop sharing, and then Bruce, I'm happy to share your slides for you, or if you want to drive, up to you.
I'll drive.
Okay.
You bet. Be sure. Are you seeing the full screen?
Looks
okay.
Good.
Yes.
Great. Thank you. Thank you, Albert. I appreciate that, and Allison as well. I look forward to the conversation coming forward here with all of us. And Zolti, it's good to meet you. I mean, oil has literally and figuratively fueled the 20th century and carrying us into the 21st century. From cars to economics to geopolitics to wars, everything in between. You might say that we live in a culture of oil, and therein lies a bit of the problem. Culture change must be one of the hardest undertakings there is for society. Oil, fossil fuels in general, shapes nations through its geographic concentrations. Hydrogen has the very real potential to alter that shaping by virtue of the potential for distributed, localized, on-site, on-demand production. Just to shape a little bit of the conversation around the culture challenge in particular, what I'd like to do is talk not so much about things you may not have known about hydrogen, but rather the strategic context that frames the movement from our reliance purely on petroleum-based energy for aviation toward what could become the role of aviation in a hydrogen economy. And so the scope I'd like to start with is, as always in engineering, we like to, we can get distracted by the thrill of technology, but what we really want to pay attention to, of course, is what problem or problems are we solving? Then why has this problem or these problems have not been solved before? Why do we think we can solve them today? What's the value of the solutions? And then finally, how do we proceed? I'm going to suggest as an hypothesis that hydrogen as an energy source for aviation is both enabled by and is an enabler of the evolution of the hydrogen economy, of course, engendering along the way the technological, infrastructural, regulatory policy, and societal transformations that go with it. Along the lines of what problems are we solving, you can ask this different ways. Why hydrogen? Well, the obvious ones are air quality, energy independence, and geographic equity. I mentioned earlier that the potential for hydrogen to become divorced from geographic locations is a very important feature of this landscape. And then finally, what appears on the horizon, it may be some decades away before we have gallon of gas equivalent pricing, but the affordability of renewable hydrogen generation capabilities, including liquefaction for aviation applications of liquid hydrogen. What I'd like to talk a little bit about is why hydrogen for advanced air mobility. We're all, pummeled every day with emails and web information about the electrification of air mobility and variously called regional air mobility, urban air mobility. I'll say a few more words about where I think the focus can be in the early days of this transformation. But why hydrogen for advanced air mobility? What I experienced in the few years I spent as Chief Technology Officer at AIAA Technologies Corporation in our development program for a liquid hydrogen powertrain, electric powertrain system for a hexcopter, aiming at about a 1,000-pound payload and a couple of hours of endurance, was the benefit at that weight class. Think 4,000, 5,000 pound maximum takeoff weight, for example. At that weight class, the benefits for hydrogen over battery for flight endurance and payload, but in the end, it's also the capacity for electric vehicles, hydrogen vehicles in particular, to have a fleet duty cycle, which reduces the number of vehicles that you have to have in a fleet to service a market. Little bit of math there. If you can refuel hydrogen vehicles in minutes rather than tens of minutes or longer, your fleet duty cycles are much more efficient. And then finally, the advancements that are forecast by reports, for example, out of Argonne National Labs not too long ago about the comparative total cost of ownership of hydrogen fuel cell electric powertrain aviation aircraft. And then, why advanced air mobility? This is a convergence. What I'm describing to you is a convergence of need and opportunity. The need is for advanced air mobility, not only sustainability from a climate standpoint, but the role of accessibility to communities and markets, and the effect of advanced connectivity, physical, in particular connectivity between supply and demand and production and consumption, and the effect that connectivity has on productivity. Just a sidebar briefly, our nation has been in a productivity decline since the 1960s. It has not slowed down. It's been very steady. It continues today. And it's a mystery for the most part, certainly to me, but to economists who study this for a living. Here we've got computers that we carry in our pockets and connect, connectivity by telecom systems and the internet and everything that goes with it. And yet we're still seeing this decline in productivity. What gives? Well, an hypothesis I'd like to offer about that is that when you can connect, as I said earlier, production with consumption and supply with demand, one of the premises in Adam Smith's book, Wealth of Nations, was that when you do so, you have a direct effect on productivity. And so perhaps there's an aeronautical hypothesis about the effect of connectivity and accessibility in markets in a sustainable way that can reverse the decline of national productivity. Just a thought. So where is hydrogen in service today? I'm fascinated to learn more and more about the implementations that currently exist for hydrogen, and some that are coming along fairly rapidly. I had been unaware there are 40,000 forklifts in the US at about 80 distribution centers, about half of which are owned by Walmart and Amazon. And all of those forklifts are run on liquid hydrogen. So there's already a liquid hydrogen infrastructure out there. And if you wanted to do cargo, for example, cargo air vehicles, between and from those distribution centers, there's a bit of a ready-made potential in that regard. The cell towers in the country have backup power systems. They had been mostly, of course, diesel gensets, and the industry is moving gradually away from those. There are 4,000 cell towers that are have backup power provided by hydrogen fuel cell systems. The numbers are small. There are only 1,300 as of 2020 buses that are hydrogen fuel cell powered today. There are a fairly small number of cars that are hydrogen powered today, and a fairly small number of hydrogen refueling stations, mostly in California today, but some developing in Massachusetts and in a few other states as the hydrogen automobile industry begins to develop some traction. An interesting one he was learning about the airport ground service equipment, or GSE, for which standards, hydrogen fuel cell power system standards, have been written and have been tested. The FAA Technical Center at Atlantic City does a lot of that work, and those systems are developing not only for airport ground service equipment that used to be run on batteries or gasoline, now moving to hydrogen, but also things like galley applications in the aircraft and reserve power systems for the unfortunate event of loss of engine power for producing electricity for onboard systems, is to have backup hydrogen fuel cell systems, for example. So there's many suppliers working with those implementations. Those same suppliers, many of them are working with developers of aviation applications, including the related standards for those aviation applications. Well, the state of the art is, let me just say, minimal today in this regard. Hydrogen fuel cell powertrain technology readiness levels, TRL scale, that I know we're all familiar with, for electric motors is probably fairly high, TRL 5 and 6. There's still much work to be done to advance electric motors, in particular. If we can get away from liquid cooling of electric motors for aviation applications, be a marvelous advance. Liquid hydrogen tanks for aviation applications are still a fairly low TRL level, as are fuel cells themselves for aviation. Of course, fuel cells for terrestrial applications are already TRL 9. But then the integrated heating and cooling systems for fuel cells as well, still a fairly low TRL level. So there's much work to be done there to move toward commercialization of hydrogen fuel cells in these aviation applications. So how should we proceed? I'm going to suggest that we start, and many are already, starting with regional, rural, exurban, emergency cargo service applications for air vehicle development. Why? Well, in my opinion, there's a great alignment of hydrogen benefits with mission profile needs. Those missions require hours of endurance and north of 1,000 pounds, maybe even north of 1,500 pounds of payload, resulting in vehicles of 4,000 and 5,000 pound MTOW class. And so hydrogen provides you with the the energy densities necessary to meet those mission needs. There are also lower technical and regulatory barriers to entry, not the least of which is airspace management in those rural, regional, ex-urban and so forth markets. There are also more than 5,000 public use airports in the nation today. And there's some interesting statistics around that. 80% of, maybe more than that, but I'm going to be conservative, 80% of the nation's population lives within a 20-minute drive of an airport. They're not big airports, of course, but that infrastructure could serve as as nodes in a hydrogen infrastructure, especially if the hydrogen infrastructure in those facilities, those airport facilities, could be ecumenical, so to speak. In other words, could serve trucks and automobiles as well, and be used to generate electricity for battery charging. Again, just a thought. Another, how should we proceed is there is an opportunity and a need for engaging in pre-competitive technology advancements through collaborative activities. Public-private partnerships have a long track record demonstrating the ability to reduce the time required to advance TRLs from the mid-scale all the way up to the commercial scale. There's a lot of storytelling in my background I can share about that from NASA programs that I was involved in over many years. Also, in those collaborative activities, leveraging existing DOE, ARPA-E, FAA, NASA R&D programs and infrastructure would be a valuable thing to do. I'll poke at my NASA colleagues a little bit by encouraging them to begin thinking about what it looks like to have hydrogen electric powertrain investments in parallel with the battery electric investments. There's a place for both. And I think it would be valuable to do that. One of the questions I was asked recently by one of my NASA colleagues was, have you done the math on, can you produce enough green hydrogen, to run even a small fleet of electric aircraft? And so the example that I'll just quote some numbers from here is that if you have a fleet of 10 5,000-pound hexcopters, and you want to produce using solar, modern, 18% efficient solar panel farm to generate the electricity to go through electrolysis to create the hydrogen and run a liquefaction machine in parallel to produce the liquid hydrogen. You'd probably store the hydrogen as gaseous and then do the liquefaction conversion on demand so that you don't have to have so much waste with boil off. But if you wanted to have a system like that at a small airport where these electric eVTOLs would be operating, it would take about 100 acres of land at current levels of solar panel efficiencies. And those efficiencies are improving. And I'm being a bit conservative. At the lower end of that scale is probably something on the order of 75 acres. But 75 to 100 acres would be enough to do the job. So the answer is yes. We've looked at the numbers. They're certainly approachable in certain geographic locations and certain, if you've seen one airport, you've seen one airport, of course. So you need to do the analysis very localized. So with that, I'll close my remarks and hand the baton back and look forward to the rest of our conversation.
Thank you, Bruce. Now let's give the floor to Zolti. We'll take the question afterwards.
Thank you. Let me see if I can. Okay, can everybody see this?
Yes.
Yes.
Okay, great. Well, first of all, thank you very much for the invitation. Title is Hydrogen in Aviation, Past, Present, and Future. So I'd like to give a short historical view on the use of hydrogen in aviation, maybe look at the current challenges and give an outlook on possible pathways forward. Before I start, let me acknowledge my colleagues, Vic Bichette, Alan Epstein, and Ed Greitzer, As a group, we had regular and frequent discussions about the 2050 Grand Challenge, and some of the data and information came out of these discussions. So the first hydrogen balloon was launched in 1783 in France. Over a decade later, this was the first hydrogen aluminum airship. The inventor, David Schwartz, had a heart attack before it could actually take off. So I think his wife joined up with Carl Berg and tried to get it working. But as you can see, there were structural challenges. If you look at the panels there, the design was flawed as the skin took most of the shear stress, leading to distorted panels, in essence, plate buckling. Graf Zeppelin, I think, acquired some of the plans, and this is the first successful airship in 1900, 13 years later. 16 gas cells made of rubberized cloth, a successful demo of the very first airship. After World War I, the Treaty of Versailles prohibited further development of airships in Germany until the US Navy commissioned construction of an airship by the Zeppelin company, the USS Los Angeles, shown here. Very impressive dimensions, 2.5 million cubic feet of displacement. And it logged almost 4,500 flight hours, so very remarkable vehicle. So just to summarize the aviation by airships, a total of 120 Zeppelins were built. The most notable ones that people know of is probably the Graf Zeppelin, 9 years of service with hydrogen, a bigger, 3.7 million cubic feet of displacement, 144 ocean crossings, transported over 13,000 people. It was long trips, right, from Germany to South America, but this was the way to travel. And then, of course, the Hindenburg. It was actually designed for helium, despite the US ban on the export of helium under the Helium Control Act of 1927. Was then operated with hydrogen. As you know, in 1937, there was the Lakehurst accident. But again, 50 passengers, a range of 8,750 miles. Now, if you fast forward to the mid-50s, it's when Lockheed was working on plans for supersonic reconnaissance aircraft, the Lockheed CL-400 shown here, or codenamed Suntan. The goal was to be faster and higher altitude than the U-2. All this enabled by liquid hydrogen. This is designed by Kelly Johnson at Skunk Works. Unfortunately, it never materialized. There were other issues. You can see the engines are on the wingtips. There's some serious yaw moment issues when the engines or the inlets unstart. This is also a challenge for the SR-71 or the YF-11 and 12 demos later. Just one shot on the mission profile. Again, a little bit shorter range than the U-2, but higher altitude at 90,000 feet. Supersonic cruise at Mach 2.5, and a sortie of less than an hour. So a very impressive mission profile. This is the engine, the PW304 or Suntan liquid hydrogen engine. And there's a person there to give you an idea of the size. There were, of course, a number of challenges that had to be overcome. As you know, liquid hydrogen is extremely cold. Atmospheric pressure boils at, I think, around 415 or 20 F. So conventional materials like steel become brittle. Of course, the advantage is the heating value is 3 times of jet fuel. The specific heat is maybe 15 times of air. So for this particular engine, I think there were 3.5 pounds per second of liquid hydrogen run to produce 12,000 horsepower to drive the fan. And of course, another challenge is the low density. So the tank volume had to be about 5 times of that for jet fuel. It ran on an expander cycle. So here's the engine and there's the cartoon. If you start on the bottom there's a liquid hydrogen pump, external. It's in essence driven by a front tower shaft. It pressurizes the liquid hydrogen to supercritical pressure. And then if you can see my cursor, there's a heat exchanger to raise the enthalpy. And then that hydrogen expands over a turbine. It's a tiny turbine. So there's a gearbox that's needed between the fan and the turbine. And then that hydrogen partially goes into the primary burner and then the rest goes into the afterburner. So basically, it's somewhat a core of a rocket engine. If you think of the compression fan being replaced, the LOX turbopump and that feed line. Here's a picture of the 12,000 horsepower reduction gear. I think turbine ran at 25,000 RPM, compressor maybe at 6,000. So an impressive piece of engineering back in the 50s, maybe the origins, the gear for the GTF. Another key enabler and technology challenge was the heat exchanger. So again, you see the dimensions there. It's almost 2 meters in diameter, An enormous amount of tubing was used. I think it was over 8 kilometers if you stretched it out. Many of the tube joints were furnace brazed. And then, the hydrogen came in, you pressurize it still at 20 Kelvin. Heat exchanger took it up to 1,000 Kelvin, and then combustion gas entered the turbine at maybe 1,500 Kelvin. So lots of heat transfer, maybe 72 million BTUs per hour, enough to heat 700 6-room houses. Give you an idea of the size of the hydrogen turbine. It's tiny. It's in essence, inside the central body. So to the left, you see the fan. And then the key or the core of it is, of course, the liquid hydrogen pump shown here. It's 2 centrifugal stages back to back. Maybe if you see my cursor over here, it's an aluminum star wheel for stress concentrations at high speed. And for those of you who are turbomachinery enthusiasts, note that they're radial blades, which of course yielded a reduced stable flow range. Another critical problem was that an impeller was required that would handle liquid hydrogen without cavitation, and adequate sealing between the high pressure liquid hydrogen at 20 Kelvin and the oil lubricated bearings. So very cold one end, very hot other end. I think 5 engines or so were built for development. But as I said, the aircraft had some hard problems like the lightweight insulation, seals, and so forth. So the CL400 was never fully built. Of course, the choice of aluminum really limited the flight Mach to 2.5. So kerosene type fuels, become viable again at Mach 3+. So, go back to the 50s, the secret enablers were titanium and the J58 convertible engine, both originating at Pratt. And in essence, they made the SR-71 possible. So by the end of the 1950s, suntan was dropped and the focus was really on the SR-71. Now, in terms of learning, hydrogen technology and all the learnings, of course, were applied to the rocket engines. So, for example, legendary RL-10, which was the first hydrogen-fueled rocket engine, was based on some of these ideas. Okay, so I think Bruce put it very well. So here are maybe some other numbers just to sort of lay out the grand challenge for 2050. If you maybe run the ICAO calculator, 1 kilogram of kerosene yields about 3 kilograms of CO2. So fuel flow on average, maybe at altitude is a order of kilogram per second. So if you multiply this figure with the number of aircraft flying at any given moment, things accumulate and escalate pretty rapidly. So there are several 100 million tons per year. So 915 million tons in 2019. If we don't do anything by 2050, this will double to maybe 1.8 million tons. So therefore, there are some very tough goals. So the IATA 2009 global target is the 50% reduction. I think in February this year, EU launched a sustainability initiative called the Destination 2050, which will require all flights within the EU and the UK to be CO2 net zero. And then with the new US administration, there's the ambitious target of a net zero economy by 2050. So this is in line with the Paris Climate Agreement. I think you all know this, but this is the current carbon life cycle diagram. So you extract carbon from the ground, you transport it, you refine it, you transport it again. There's more distribution. And then you use it as an energy carrier in an aircraft. So CO2 emissions occur in each and single step here. So the takeaway is we have to move from fossil fuels in the next 30 years, and time is really short if you contrast that to a life cycle of an aircraft or a lifetime, maybe 20 to 30 years. This is a chart. It's a little outdated. It's maybe 10 years old, so the numbers might change a little bit, but the message is still the same. This is the global civil fuel aviation fuel consumption. About half of CO2 is from long haul. So addressing the 2-seaters or even regionals will have some impact, but there are much bigger challenges with the single and the twin aisles. So what are the options? Of course, lots of attention has been given to battery electric and hybrid electric concepts. In every, no matter what the energy source, there will be CO2. And the bottom line is that batteries need to be charged. So even if you use renewables, they will have a small amount of CO2 emissions. To put things in perspective, what this chart shows, this is from Alan, is the aircraft usable energy density. So the y-axis is the usable energy density, And then on the x-axis, you have the year. The top is piston engines, turbofans, turboprops, with a 0.7% growth per year. And then the bottom is the batteries plus electric motors, the whole powertrain for different battery chemistries. Okay, and this is up to today. And you see there to the right, there's some battery cells in development. But even those, and if you extrapolate, the gap in usable energy density is an order of magnitude. So this is really tough to close. This here is the engine efficiency for different type of aircraft engines. And if you look at the x-axis, that's size. So to the left, you have the smaller engines, piston engines, less efficient. And then the green are the airliners at altitude, very efficient devices. As I said, batteries need to be charged. So if you look at the world grid to battery, that's that point here, that's maybe at 40-ish%. And this is the equivalent aircraft engine carbon dioxide impact. US is doing better. And then Singapore, I think there's 95% of energy in Singapore is from natural gas. So they're at the very high number there, competitive with the airliners. So how about hydrogen? There are, of course, several pathways with different energy sources, some more, some less, or no carbon intensive, not much carbon intensive than others. If you now look at the different types of hydrogen, today, maybe in the future, today we have gray hydrogen, Gray hydrogen to the left is hydrogen produced using fossil fuels, maybe such as natural gas. And I think about 95% of hydrogen today is produced as gray hydrogen. And what's to come is the blue hydrogen. So the source is a fossil fuel and the CO2 released is captured. So we call this the blue. There's of course other ways to do it, to stay or to meet the low carbon threshold. And that's maybe to use non-renewable energy sources such as maybe nuclear power sources. And then, the end goal is the green hydrogen. And that hydrogen not only meets the low carbon threshold, but is generated using renewable energy sources such as solar or wind. Now, if you look at what does it take to make liquid hydrogen? So these are rough numbers, and these are maybe current numbers, and people working really hard at technology to improve these. But I just wanted to put these in perspective to show you where we think we are now and what's the gap to close. So if you start with 100% energy, renewable, there's broad brush electrolysis and liquefaction. You use about 50% to get to the liquid hydrogen. And then there's a couple of choices. You could run a gas turbine on hydrogen. I mean, I showed you the suntan. Of course, there's other, this is optimistic because it doesn't include transportation and boil off loss and so forth. But let's say a 50% efficient gas turbine, that would give you a net efficiency to shaft about 25%. If you use a fuel cell, maybe at 50% efficiency, maybe a 90% effective efficient electric drive, or maybe at 23%. So again, these are current numbers. Everybody's working hard to improve these. Now, another challenge is storage. So two choices, gas versus liquid. The transportation industry, of course, has been demonstrating some very sophisticated technology. So the left is from Toyota. That's the Mirai fuel cell car. And if you look at it, the hydrogen's at 700 atmospheres and the fuel mass fraction is only 6%. If you look at the Boeing Phantom I on the right, the vehicle is in essence the fuel tank, right? And fuel mass fraction is 53%, but you have to keep it very cold. So challenge is either very high pressure, super low mass fraction, or very low temperatures. And again, a challenge with the size. And the other challenge, of course, is the boil off, right? So for this tank shown here, the estimated boil off is maybe 2% per hour. So you lose maybe close to half per day. This is a very complicated chart. I'm not going to go into the details, but the message of the chart is to say it's complicated. So the automotive folks have spent a tremendous amount of time developing these concepts. And this is one of the state-of-the-art liquid hydrogen tanks. And it's more than just a tank. You've got outer, inner, there's heaters, heat exchangers. So it's a very complicated device. And again, if you look at the state-of-the-art, fuel mass fraction maybe of 7%. Okay, so going back to aviation, what we have here is different options. You got the Jet A, and then you got the liquid hydrogen. And both gravimetric energy density and volumetric energy density matter. So for going to hydrogen, of course, the gravimetric energy density, that's the light blue, increases, as we said, but the challenge is the volumetric energy density. So if you look at where the fuel is, it's stored in the wings, there's just not enough wing. So we have to store the liquid hydrogen in the fuselage. And then the gaseous is very challenging if you look at the numbers. So again, just sort of pasting these things together, you take maybe state-of-the-art Fanami tank, look at the Beach 1900. This is, how low-key might need 2 of those tanks for that mission. I'm not going to say much more about this, but there are some plans and ideas for other aircraft concepts. And the challenges, of course, include the low fuel density. You have to keep things cool, the cryogenics. Although cryogenics do have advantages, you might be able to run at lower voltages, less loss. And then you have hydrogen near to the passengers and so forth. So maybe let me close, because the panel is about looking into different possibilities and maybe just stimulating a conversation here. Sustainable aviation fuel is maybe another option. There are very different pathways for SAF, different sources such as waste or biomass. Again, the energy source could be renewable or nuclear, but yes, there is carbon dioxide impact. So possibly best we might be able to do at some point is this diagram here, which is the carbon life cycle diagram for sustainable aviation fuel. One example could be the so-called electrofuels. So you would use renewable electricity to convert CO2, which you either capture from the industrial processes or directly from air into SAF. And you could deploy this anywhere in the world, but of course, initially likely near existing industrial facilities or close to sources where you have the renewable energy. Things are in the works. Some of the technology is being demonstrated at lab scale, showing promise, but much more work is needed. Some parts are very mature and in common use, such as the Fischer-Tropsch processing, but other challenges remain, especially scaling things up. And of course, cost is always a big driver, maybe the driver. This is a chart from the Waypoint 2050 document released last September, I believe. If you look at the charts, it's a little complicated, but this is the cost, and then this barrel here is the fossil jet fuel price spread between 2000 and 2019. And then you get different choices, HEFA and other kinds of sustainable aviation fuels. And the green powdered liquid, I think that's like electrofuel, very costly, I don't know, maybe factor 4 or 4.5 now. So the different columns are different years. But this is a projection. The aim is, of course, to reduce this, and the outlook says that hopefully, well, hope is not a good strategy, but the aim would be to dramatically reduce cost and to improve technology. So one last slide, and I'll stop. So if you summarize it all, what's the outlook? Batteries might not be feasible for airliners. Yes, there are demos for smaller vehicles, absolutely. But if we talk airliners, there's a real challenge. There is no battery technology that could yield the energy density, and also charging the batteries requires a green grid. Hydrogen is maybe a vision at this point, not yet a reality. Taking maybe strong words might not be practical, and it's too far away. Doesn't mean that we shouldn't work on it. But again, if I take the perspective of airliners, this is a real challenge, safety, scale, and again, the investment is huge. And again, put this in perspective with the aircraft life cycle of 10 to 30 years. So better airplanes help, but we still have to run on low carbon energy. So the right is SAF. It's here now. There are many paths still to be worked out. What's the best way to go? Main challenge is scale. And again, there's of course cost for capacity. And as I said, there's lots of technology still required to reduce the cost. So with that, thank you. And I'll hand it back and see how we're doing on time.
Thank you very much, Zolti. The two panelists now have covered really a very broad range of issues, which is good because it could start the conversation. My first question to Bruce. Let's see if I understand what you said in terms of the market segment that you focused on, which you called it regional, rural, etc. So are we talking fundamentally about small planes up to, let's say, an Embraer type, as opposed to not the 737? Is that a correct statement?
That's correct. Yeah, I'm unaware that the kinds of trade-off studies have been done to figure out where the boundary is between efficient battery solutions and the requirement for liquid hydrogen powertrain solutions. But just based on our experience, my past experience, I suspect that boundary for the hydrogen solution being favorable starts somewhere at payloads of around 1,000 to 1,500 pounds. And I don't know where the upper limit of that is, but I suspect that it's not much north of an air vehicle gross weight, I'm thinking fixed wing here, of somewhere in the neighborhood of 20,000, well, 19,000 pounds would be a convenient number to pick because of the new rule, the new regulations under Part 23 for airworthiness certification. And so you're seeing already companies out there like Zero Avia, like Universal Hydrogen, focusing in applying hydrogen powertrain solutions to the class of vehicles, say like the Dornier 228 or the Dash 7 de Havilland Dash 7 Dash 8 class of aircraft. In part because of the point I was making that there's a natural alignment, I would say, between the energy requirement for those mission profiles and the availability of that energy from a hydrogen fuel cell powertrain system. And so that's a long answer to your question. The short answer is yes.
Yeah, clear enough. So basically, we understand that it will work for very small aircraft, but you don't know the upper limit.
Right.
So of the small. And I would like to go to Zolti, who kind of looked at the problem from the other end and said that the big planes, it's a nice vision, but liquid hydrogen aircraft may not work very well in the big plane, at least within 2050. Could you go down the scale and say where it might fit?
Well, you saw that picture with the Phantom I tank, right? That's sort of a state-of-the-art tank, an advanced tank. And if you take that Beech 1900, you could possibly see if you could fit those tanks, right? But that's just part of the challenge. So I don't have a good answer of how small you could go. I think as Bruce said, I think that the numbers need to be done and a rigorous study where the breaking line is. Just contrasting this with electrified aviation, we did a study under an NASA contract where we looked at exactly this question, but it was for hybrid electric to see what missions could you actually do with an electrified system, and where would you go with batteries only and the hybrid electric. So I think a similar study here. And I believe some people are already thinking hard about this and are working on it. But yeah, that's to be, I think, decided.
Pushing further the same issue. Does that mean that the net zero by 2050 ain't going to happen? It might happen for small planes, but it's not going to happen for aviation in general.
Albert,
do you folks agree to that?
Well, I don't think I can predict the future, right? All I can say is that it's real hard challenges. But look, we're all engineers and we do love challenges. And I'm not saying we should stop not worrying about these things and just shelve hydrogen. But I think, taking the hydrogen avenue, some technologies must be demonstrated. And along those lines, how would hydrogen by itself on board, and what would be the size? I think those questions need to be answered. So I can't give you a straight answer. If you look at the charts that I showed, look at the numbers just at face value, it's really hard. Time is short. Time is really short, and lots of things have to happen by 2050.
Bruce, you want to comment on that?
I do. So there's a lot going on in the technologies of all of the components affecting the total system efficiency for HFC system, hydrogen fuel cell systems. Zolti, you showed some data about storage efficiencies. I'm familiar from my past work with the advancements in state-of-the-art of storage efficiencies, in particular, for example, with some of the polymer technology storage devices that were getting north of 20% mass fraction for liquid hydrogen storage, and fairly prosaic titanium. Double hull systems were north of 15%, even up to about 19%. So, and that progress continues. The stack efficiencies themselves are making progress as the industry focuses for the first time, actually, from away from just terrestrial applications where you didn't care so much about weight to airborne applications where flight weighting matters and maintaining the efficiencies. So stack efficiencies have been improving just in the last, I would say, 3 or 4 years, from sub 1.0 kilowatts per kilogram for a stack performance scale up to 50 to 75% better than that, just within the past 3 or 4 years, and continuing. And there's a fair amount of work. One of the questions in the chat room here is thoughts about storing hydrogen in metal hydride systems. Absolutely, that looks fascinating. There ought to be some research on that, but there is some research on that. In the Southeast US, there's a Southeast Hydrogen Alliance that involves some of the universities in the Carolinas looking at alternatives for hydrogen storage. I mean, if we could store hydrogen in solid form on board and then use that, there could be some potential advantages operationally as well as efficiency-wise. I don't know how that works coming along. I've been working in other activities for the past year, and I find every time I peek back under the hood, there's something new happening. The advancements in what they call balance of plant. It's everything that sits on top of the stack to make the stack operate, including compressor performance. The compressors that were available in the market off the shelf, so to speak, as little as 2 or 3 years ago, were designed for ground applications. Well, in an aerial application, you've got to have an aeronautical based efficiency for compressor performance. That and the companies that do turbochargers for aircraft are interested in doing some of the work to make advancements there. All of that plays into ultimately seeing stack efficiencies maybe exceeding 2.0 kilowatts per kilogram. There's some speculation out there in some of the high temperature PEM fuel cell stack system research at the laboratory level that's showing even north of 3.0 kilowatts per kilogram for stack efficiency, stack performance. So all of that is to say that there's a tremendous amount of advancements that we can expect that are well within the laws of physics for the way these systems can work and work better than they do even today.
Yeah, and I'm in full agreement, Bruce, with that. Absolute agreement. And as you mentioned, there's other challenges if you go to altitude, right? Total environmental system. So that's still to be demonstrated, though, right? So I'm with you on that. Absolutely, no question.
I also look forward to all of these advancements. But let's take two examples or two issues. One is the impact of a liquid hydrogen tank on the design of the plane itself. And some of the pictures that were shown, you would have a fuel tank in front and one in aft with the passenger in between, something that historically the FAA would not allow because they like contact between the cockpit and the passenger. I'd like Bruce to talk a bit more about what impact there is on impact of the fuel tank on the plane design, and for Zolty to address the same impact on the engine part.
So on the
only 2 minutes, please, not too long.
Yeah, it's 2 minutes. So certification is underway with some of the companies who have already achieved their what's called the G1 document from the FAA, which defines rules and means of compliance, and they're complete. In other words, the rules have been written and the means of compliance have been written for how you certify these air vehicles. They haven't done it yet, but the FAA has accepted the documentation on the process. That's a big step. And so again, for small aircraft, the crash worthiness testing that will have to be done will be the proof of the pudding on liquid hydrogen tanks. The tanks themselves have been shown to be very crash worthy, let's say. So that seems to be less of a concern right now for the FAA and for the developers. And the tank, a tank for a vehicle of the sizes that I've been talking about is probably going to be somewhere around 300 to 400 liters, right? And that would be, for a payload north of 1,000 pounds and an endurance probably north of a couple of hours with an eVTOL configuration. So that work is underway. The FAA is being very forward-leaning about how to move these concepts ahead.
Yeah, so on the engine side, I'm not going to go back to the technological challenges. Some of them have been demonstrated as I showed, but let me maybe comment on the regulatory side of things. I mean, as Bruce said, same thing for the engine. There's huge challenges, and let me contrast it with SAF. Right now, it's maybe 50% of a blend, allowed. People are pushing to 100% SAF. Why is it 50%? Because there's several decades of experience with kerosene. Right, it's sort of the risk averseness of the industry, and I mean, one huge hurdle to overcome is, as Bruce said, is the regulation. So again, I don't know what the timeline is, but in my mind, it always starts with the demonstration and demonstrating things work, and then getting traction and then moving forward. So I would not start with the regulation. I would start with the technology and push forward with demonstrations.
Okay, sounds good. Now we have a question from the audience. What are your thoughts on Airbus's Zero's E initiative? Do you think they'll be able to meet their goal of a hydrogen-powered commercial aircraft by 2035?
Well, I don't think, let me maybe start. I don't think the plan is to meet it by 2025. I think there's a decision point.
2035.
2035, okay, yeah. So I think the decision point is maybe 2025 to see which pathways to take. I think, again, let's let the numbers and the data speak. And I see Amanda is on the call, so she might be a better person to actually speak to this question.
Please go ahead, Amanda.
Not sure if she can.
I might have.
Allison,
I can
could you allow her to speak?
Yes,
yeah.
I can
Could
do
you
that.
give her?
Yep.
Amanda is from Airbus.
Everyone, can you hear me?
Yes, you can.
Yeah.
Well, I thank you for the question. And by the way, a great presentation, really enjoyed it. And with regards to Zero E and Airbus, we're moving forward. We're pushing technology. We're evaluating what's out there. When you start tugging at the little, the little strings out there, you find some real gems. And when you start putting them all together, we've got about 4 years till we have to make our decision. We think we're going to get there. It looks very good.
Sounds good. Let me raise another question, since we're talking about technology, and there are efforts in the UK to use the cooling ability of the hydrogen to improve the electrical and the motor performance by essentially replacing current technologies with partially superconducting or fully superconducting equipment. Any thoughts on that?
Who was that question to?
Open to the floor. Amanda, if you would like to answer, go ahead.
Well, Airbus is currently engaged in a program to actually examine that. We're going to be doing ground tests in the next 2 years. And the Ascend program will be looking at using cryogenics to lower the resistivity through superconductivity. And again, if that looks good, then we expect to be doing some full up airborne trials in the next several years.
Well, this is an example where one can use the natural properties of liquid hydrogen to some advantage, which is good. So it's not just trying to use liquid hydrogen because it reduces carbon, but it's got some other technical advantages.
Helps with air conditioning as well in these bubble cockpits that we are designing.
So to sum it up, Albert, I think there's no silver bullet, right? Many things have to come together to make all this happen.
Yeah, I understand that fully. What surprised me a little bit is when the politicians put a goal that may be not achievable. And as you recall, there have been several of these over the years with hydrogen and these different waves of the hydrogen economy, etc. And then when you oversell it, then it falls on its face. And it'd be good to kind of provide some perspective to plan for the right target, so to speak. Now let's see, any other comments on that point? We have questions from the audience. Any thought on storing hydrogen as ammonia on the aircraft?
Yeah, I commented a little bit about that earlier. Ammonia or metal hydrides is a very interesting technology. It's been about 10 or 15 years, maybe longer, since the research into that particular approach was done, and it's time to open that drawer again and take another look at it in context of modern needs. There's a fair amount of work underway down in, as I mentioned earlier, in the Carolinas at the universities in alternative storage technologies. I'm not deeply familiar with the state of the art currently where they're at. I just know it's underway.
Is Airbus working on that? Did Amanda leave us?
You guys keep putting me on the spot. We've looked at, we evaluated, I'll just say many different ways, many fuels. And that was one. And for a variety of different reasons, the favor went towards liquid hydrogen.
Where does ammonia fit?
I'd put it on a TRL scale to make sense out of it. Where liquid hydrogen powertrain systems, are hovering around TRL, between 4 and 5. Solid hydrogen storage technology for an aeronautical application is probably still at about a TRL 2.
And ammonia is highly toxic. So any small leakage is not very desirable.
Yeah, there was one question, and that's an important point. One of the questions in the chat box was about the unintended, how did you word it, Hero, consequences of side effects of hydrogen. The beauty of hydrogen is it's non-toxic, it's not poisonous, it's cold, it has its own risks. But these are risks for which standards have been in practice now for years in the terrestrial applications and proven to be as safe or safer in some respects than liquid fuels are. And so avoiding toxicity, would be a pretty important feature of the design, framework that you work in. Now,
hydrogen is not toxic. However, in in an airplane, you have vibration, and of course, there's always the potential for crash. And I'm sure the tanks could be built to be strong enough, but the connections can leak. And if you leak hydrogen inside an aircraft, that would not be very safe. Not so good with any jet fuel either, but hydrogen, particularly the leakage potential, the seals, all of that would have to be very different to ensure that this doesn't happen.
You work hard to make that probability as small as possible, and then you also design around it. So you know the beauty of hydrogen from that standpoint is it escapes upward at about 45 miles an hour, right? So you just have to have escape paths built into the airframe for that eventuality. So we're not talking about pressurized aircraft here. We're talking about unpressurized aircraft. So that kind of issue can be built into the certification processes and is being built in.
And if you have the fuel tank in the back close to the engines, then you could have a firewall if you want, or a pressure wall to ensure that. However, when you talk about fuel tanks in the front and the back, I don't see how you could prevent a leakage, how you could vent out a leakage effectively.
Yeah, I mean, so the configurations with which I'm familiar only have a tank in the rear part, or tanks in the rear parts of the vehicle. And so, you know, the venting requirement is built into the certification standards.
Speaking of certification, now I know NASA and the FAA is working very hard to develop the new the National Airspace System. And that could take quite a few years to figure out what to do. In the meanwhile, when you apply for a type certificate, if you get it, does that give you automatically the right to fly, or what?
You build the operating limitations into the type certificate application. And for example, you could certify the aircraft to fly VFR only at first, and then VFR and IFR later under the same certificate application. So there will be the early the early operations of these aircraft will be well within the confines of the existing airspace architectures and procedures.
That sounds good. We have one last question from the audience. It's a very long question, so bear with me as I read it. At the Naval Postgraduate School, we began to study a hydrogen OTEC plant ship as part of a mobile offshore platform. The top of the platform is an airstrip sized to take off and land for a C-130. The OTEC plant ship platform, a model, it's very hard to read a long question in a chat box. So it seems like it produced a very large amount of hydrogen in 100 hours, equivalent to 60 megawatt OTEC. Very impressive. So the Navy is doing that. And I see they selected a C-130, I suppose, because of its size. Then you can fit in a hydrogen tank. And what I'm getting from all of that is, yes, we can predict the future, but there are niches where hydrogen will make sense, and there are others where it may not. And I go back to Zolty's SAF fuel, which maybe a combination of that and hydrogen is probably the answer that will make everybody happy and minimize emissions. On that note, if anybody else want to make a closing comment, please go ahead.
Oh, just thank you, everybody. This is a great panel, great questions and good discussion. I really appreciate it for having me. Thank you.
You're welcome. How about you, Bruce?
Yeah, I like this recent article in Aerospace America on the challenges of the way to net zero. The fate of the planet cast is hanging in the balance. Check. Potentially insurmountable technical obstacles. Naturally. A seemingly impossible deadline. But of course. And I encourage everybody to read Ben AIAA-NE's editorial at the beginning, where he basically says aviation is long overdue to embrace bold innovation. Well, here we are.
Okay, that was a very nice closing comment. I want to thank the panelists as well as the audience for their participation, in particular Amanda, and thank you, Allison, for hosting the meeting. And we will close it right now. Good night, everyone.
Good night. Thanks, everybody.
Thank you, everyone.
Bye.
If you didn't have your question answered, feel free to reach out to AIAA New England, and we will do our best to help you get those answers.